Tonight, a question sits at the edge of what physics can currently answer, not at the edge in the way that most unanswered questions sit there, waiting for more data or a cleverer experiment. At the place where the tools physicists normally use to answer questions begin to reach the limits of what they can clearly say, and where the answers that come back are genuine and confirmed, and strange enough that the people who found them are still working out what they mean. The question is whether the speed of light is truly the final boundary, whether the universe has anything beyond it, in any form, accessible through any door that the mathematics might have left unlocked. Get comfortable now. Let whatever the day asked of you set itself down somewhere outside this room. The question we are following tonight has been running in physics for more than a century, and it is in no hurry. It will wait while you settle in. Here is what tonight is not. It is not a story about a secret discovery that overturns everything. It is not a story about a breakthrough being suppressed or a technology that is almost ready. The honest version of this question is more interesting than any of those stories, because the honest version is still genuinely open. And genuinely open questions are the rarest and most valuable things that science produces. What we are going to follow tonight is the real shape of the question. The experiments that have produced numbers that should not exist. The mathematics that opened a door that nobody expected to find. The confirmed phenomena that sit at the boundary of full understanding, and the honest account of where all of it leads when you follow it carefully, without overstating and without dismissing, to the edge of what physics can currently say. By the time we arrive at that edge together, the speed of light will feel different to you, not smaller, not conquered, different in the way that something feels different when you have walked its full length and found that the surface is more textured than the simple description suggested. Let your breathing slow. The universe is very old and very patient. Tonight, we move at its pace. Before anything else tonight, we need to spend some time with the speed of light itself. Not the number. The number is easy. 300 million meters per second. You have heard it before. It passes through the mind without leaving much behind. What we need is the story of where that number came from. Because most people carry a slightly wrong version of that story, and the slightly wrong version makes everything that follows harder to feel. The speed of light was not discovered by measuring how fast light traveled. It was not found by Einstein. It was found by a Scottish physicist named James Clerk Maxwell in the year 1865, and it arrived wrapped inside a discovery so surprising that Maxwell himself took time to accept what his own equations were telling him. Maxwell was not looking for it. He was trying to do something more modest. He was trying to unify two forces that physicists had been studying separately for decades: electricity and magnetism. By the 1860s, enough experimental work had been done on both that a serious mathematician could gather the results and arrange them into a coherent set of equations. Maxwell did exactly that. He took the best experimental measurements of his era and cast them into mathematical form. And then he let the equations speak to each other. What they said was not what anyone expected. Electricity and magnetism were not two separate things. They were two aspects of a single phenomenon. Disturb one, and the other responded. And the disturbance propagated outward through space as a wave, at a velocity that Maxwell could calculate directly from constants already embedded in his equations, constants that had been measured in quiet tabletop experiments with wires and coils and batteries, with no reference to light at all. The number he calculated was approximately 300 million meters per second. He recognized it immediately. Astronomers had been measuring the speed of light by independent methods for nearly 2 centuries. Using the timing of Jupiter's moons and the aberration of starlight, the values they had found clustered around the same number now appearing inside Maxwell's electromagnetic equations. The agreement was too precise to be coincidence. Maxwell wrote to a colleague that he could scarcely avoid the inference that light itself was an electromagnetic disturbance propagating through the field according to electromagnetic laws. Light was not a separate phenomenon from electricity and magnetism. It was the wave that electromagnetism naturally produced. Rest with that for a moment. A physicist doing tabletop experiments with wires and coils stumbled onto the speed of light. Nobody sent him looking for it. The universe simply put it there, inside the mathematics, waiting. But here is the part that nobody had asked for and nobody was prepared for. In Maxwell's equations, that velocity appeared as a constant, not relative to the source of the light, not relative to the observer, not relative to any medium, simply as a number, fixed, built into the mathematics of electromagnetism itself. This was a serious problem in the physics of Isaac Newton, which had described the mechanical world beautifully for 2 centuries. Velocities added the way common sense said they should. A ball thrown forward from a moving train traveled faster relative to the ground than the same ball thrown from a stationary position. That was not a theory. That was how the world worked. Maxwell's equations said the speed of light did not work that way. For 40 years, physicists tried to resolve this. The most popular solution was the luminiferous ether, an invisible medium filling all of space, which would serve as the reference point for Maxwell's constant. If light was a wave in the ether, then the constant velocity was the velocity relative to the ether, and the problem dissolved. In the year 1887, 2 American physicists named Albert Michelson and Edward Morley set up an experiment in Cleveland to detect the ether. If Earth was moving through it on its orbit around the Sun, light sent in the direction of that motion should take measurably longer to make its round trip than light sent at right angles to it. Their instrument was sensitive enough to detect the difference. They found nothing, no difference in any direction, at any time of year. The physics world sat with this result for 18 years. Then, a 26-year-old patent clerk in Bern, Switzerland, working through the implications of Maxwell's equations in his spare time, wrote a paper that dissolved the problem entirely by reframing what space and time actually were. His name was Albert Einstein, and what he proposed in the year 1905 was not a correction to Maxwell. It was a correction to Newton, specifically to the assumption that time was universal, flowing at the same rate for every observer everywhere. What if that assumption was wrong? What if time itself was not fixed? What if the rate at which time passed depended on how fast you were moving? And what if the speed of light was constant, not because of any property of light itself, but because it was the speed at which causality propagated, the maximum rate at which any event could influence any other, built into the structure of space and time themselves? If those things were true, then the Michelson-Morley result made perfect sense. Of course, the speed of light was the same in every direction. It was a feature of space-time, not of the medium it traveled through. Everything else followed from that. Time dilation, length contraction, the equivalence of mass and energy, and the consequence that matters most for tonight. As an object with mass accelerates toward the speed of light, the energy required to push it further increases without limit, not because of friction, Not because of engineering difficulty, because of the mathematics of space-time itself. To reach exactly the speed of light, the energy required is not very large. It is infinite. Infinite energy does not exist in a finite universe. The wall is not a wall of technology. It is a wall of consequence, derived from the same foundations that give us atomic clocks and GPS satellites and every particle accelerator ever built. The wall is real. It is not going away, and the reason it matters to understand what the wall is made of, not just that it exists, is that it tells you precisely where a loophole might be found. Einstein's speed limit applies to one specific thing: objects moving through space. It says nothing about what space itself might do. That distinction is narrow. It is mathematically precise. And it is the door through which the rest of tonight passes. Now, before we reach warp drives and quantum experiments and the confirmed phenomena at the frontier of physics, there is something worth knowing about why this question is being asked again right now, in this particular era of science. The reason is that several independent lines of research in quantum physics, in cosmology, and in precision measurement have each arrived at results in recent decades that sit uncomfortably close to the boundary. This question is about not discoveries of faster-than-light travel, something more interesting: confirmed results that the original formulation of the speed limit did not fully anticipate. Results that have made careful physicists look again at what the boundary is actually made of. Those results are what tonight is really about. We will reach them one by one. But first, we need the full story of the wall. There is a thought experiment that Albert Einstein said he first had at the age of 16. He imagined riding alongside a beam of light, not near it, exactly alongside it, keeping pace the way you match speed with another vehicle when both are moving at the same velocity. He asked himself what the light wave would look like from that position. The answer, when he sat with it carefully, was that it would look frozen, a stationary ripple in the electromagnetic field, oscillating in place, going nowhere. But Maxwell's equations did not permit a stationary electromagnetic wave. It was not a valid solution. The picture was internally inconsistent. Something in the ordinary understanding of motion and speed was wrong at a level that no one had yet located. It took him 10 years to find what was wrong. The paper he published in the year 1905 argued that the laws of physics must look the same to any observer moving at constant velocity, regardless of how fast that velocity is. This sounds almost obvious. The consequences it produces are not obvious at all. The first consequence is time dilation. Two observers moving relative to each other do not agree on how much time has passed between two events. The faster you move through space, the slower you move through time. Not as a feeling, not as an illusion, as a measurable physical fact. Let that settle for a moment. Time itself runs differently depending on how fast you are moving. This is not speculation. In the year 1971, physicists Joseph Hafele and Richard Keating loaded cesium atomic clocks onto commercial airliners and flew them around the world in both directions. Then compared them with identical clocks that had remained on the ground at the United States Naval Observatory. The traveling clocks came back running differently, by exactly the amounts that Einstein's equations had predicted, and it is in your pocket right now. If you have a phone, the satellites of the Global Positioning System carry clocks that run at slightly different rates than clocks on the ground, because of both their velocity and their distance from Earth's gravity. Without daily corrections for these relativistic effects, the position your phone calculates would drift by several kilometers within a single day. Relativity is not a theory in the casual sense of the word. It is an engineering specification that navigation depends on. The second consequence was length contraction. Objects moving at high velocities are shorter in the direction of their motion, as measured by a stationary observer, not as an appearance. As a geometric consequence of the structure of space-time, the third consequence was the one that sealed the wall. As an object with mass accelerates, its resistance to further acceleration increases. To push a mass to 90% of the speed of light requires an enormous but finite amount of energy. To push it to 99% requires much more. Each additional fraction costs more than all the fractions before it combined. To reach exactly the speed of light, the energy required is infinite. That is the wall. A wall of mathematics, derived from the structure of space and time, tested from so many independent directions, across so many different systems, that its core result is among the most secure conclusions in all of science. And yet, Einstein spent the last 2 decades of his life troubled by a feature of quantum mechanics that seemed to sit in uncomfortable proximity to everything he had built. Not because it violated the speed limit directly, but because it described correlations between distant particles that appeared without any signal traveling between them, in a way that no local, classical explanation could account for. He called it, in a letter to a colleague, spukhafte Fernwirkung, spooky action at a distance. He believed it was a sign that quantum mechanics was incomplete, that a deeper theory would eventually restore order and locality to physics. He did not live to see the experiments that showed he was wrong about this specific point. But before we reach those experiments, we need to understand the loophole that changes the geometry of the entire question. The wall Einstein built has a specific shape. It applies to objects moving through space. And space, as general relativity would reveal, does not have to hold still while they do it. 10 years after special relativity, in the year 1915, Einstein published a second theory, where the first had been about motion at constant velocity. The second was about acceleration and gravity, and what it said about gravity was something no one had said before. Gravity is not a force. It is the curvature of space-time. Mass bends the fabric of space and time around it. And what we experience as the pull of gravity is simply the behavior of objects following the straightest possible path through a curved geometry. The sun does not pull the Earth through empty space. The sun curves the space-time around it, and the Earth follows that curve. The way a marble rolls around the inside of a bowl, not because something is pulling it inward, because curved geometry defines what straight ahead means. This was confirmed in the year 1919, when the British astronomer Arthur Eddington observed starlight bending around the sun during a solar eclipse, deflected by exactly the amount Einstein had calculated. It was one of the great experimental confirmations in the history of science, and it introduced something into physics that has never quite settled. If mass curves space-time, then space-time is not a rigid stage. It is a flexible fabric. It can be bent, stretched, compressed, and distorted. And a flexible fabric has properties that a rigid one does not. Among those properties is this: the speed limit of special relativity applies to objects moving through space-time. It says nothing about how the space-time itself might behave. The expansion of the universe is the clearest demonstration of this distinction that nature provides. Edwin Hubble established in the year 1929 that distant galaxies are receding from us, and that the farther away they are, the faster they recede. The most distant galaxies in the observable universe are receding at velocities that exceed the speed of light by a large margin. This does not violate special relativity. Those galaxies are not moving through space at superluminal velocities. The space between us and them is expanding, growing larger, carrying the galaxies with it the way raisins in a rising loaf of bread move apart, not by swimming through the dough. Because the dough itself is growing, the expansion of space has no speed limit imposed by special relativity. The constraint applies to motion through space. The behavior of space itself is a different question, governed by general relativity and the distribution of energy within it. This distinction sat in the cosmology textbooks for decades, understood by specialists and essentially unnoticed by anyone thinking about the problem of interstellar transportation. Breathe in slowly. The universe is expanding faster than light in every direction around you right now. Not by anything moving, by space itself growing. That is a fact of the cosmos you live inside, and most people go through their entire lives without ever quite feeling the weight of it. Then, in the year 1994, a graduate student in Cardiff, Wales, noticed this distinction and asked what it implied. His name was Miguel Alcubierre. He was working on a doctorate in general relativity, and he was, by his own later account, a fan of science fiction. He had grown up watching Star Trek and its fictional warp drive, a propulsion system that moved ships across interstellar distances, not by accelerating through space, but by warping the space around them. He asked a question that was either very naive or very precise, depending on how you look at it. Not whether a warp drive was physically possible, something more specific. Whether the equations of general relativity admitted a solution that looked like one, whether the mathematics of space-time curvature could describe a bubble of flat space-time moving through the universe at arbitrary velocity with its contents undisturbed inside. He worked backward through Einstein's field equations. He defined the geometry he wanted first, a bubble of flat space-time moving through the universe, with space compressed in front and expanded behind. Inside the bubble, space-time undistorted. A crew would feel nothing unusual. No acceleration, no tidal forces, no time dilation relative to the universe outside. They would simply be sitting still while the space around them moved. He found a solution. It was published in the journal Classical and Quantum Gravity in the year 1994. 9 pages long, mathematically rigorous, checked by colleagues, confirmed to be correct. Not a fantasy, not an error, a genuine solution to Einstein's equations, in the same mathematical category as the solutions that describe black holes and gravitational waves. The paper came with a price tag. Working out what energy distribution Einstein's equation required to produce the bubble geometry, Alcubierre found the answer was exotic matter. Matter with negative energy density, a substance that pushes space-time apart rather than pulling it together, something that had never been observed in any laboratory in any useful quantity. But the geometry was real. The loophole existed in the mathematics. Rest here for a moment. A graduate student watching science fiction television found a legitimate solution to Einstein's equations that describes a faster-than-light bubble. The mathematics says this shape exists. What remains, a guess of whether the universe stocks the ingredients. That question will follow us through the rest of tonight. There is a rule in classical physics that feels as solid as anything in science. To get from one side of a barrier to the other, you need enough energy to cross it. A ball rolled toward a hill climbs as far as its energy allows. If that energy runs out before the summit, the ball rolls back. It does not find a shortcut. It does not pass through the hill. It returns to where it started. This rule is so deeply connected to ordinary experience that when quantum mechanics suggested it might not always apply, the physicists who first encountered the idea spent years checking their mathematics before they believed it. Quantum mechanics, developed through the 1920s by physicists working across Europe, described subatomic particles in terms of probability waves. A particle did not have a definite position and velocity the way a billiard ball did. It existed in a state described by a wave function that encoded the probability of finding it in any particular location. When you worked out mathematically what happened to this wave function when a particle encountered a barrier, the equations produced something that violated every classical intuition. The wave function did not stop at the wall. Inside the barrier, it decayed exponentially, growing smaller with each unit of distance. But it did not reach zero. On the far side of the barrier, the wave function reappeared, diminished but present, which meant there was a real, calculable probability of finding the particle on the other side of a barrier it did not have the energy to cross. This is quantum tunneling, and it is not theoretical curiosity. It is the operating principle of the sun. Without tunneling, protons in the solar core could not overcome their mutual electromagnetic repulsion to fuse together and release energy. Every ray of sunlight that has ever fallen on this planet arrived because quantum particles violated the classical rule about barriers. Let that settle. The sun shines because particles do something that classical physics says is impossible. Tunneling is also in the walls of your home, in every electronic device you use, in the scanning, tunneling microscopes that image individual atoms on a surface. It is one of the most confirmed phenomena in all of physics. For decades, though, no one had asked a question that sounds simple but turned out to be deeply contested. When a particle tunnels through a barrier, how long does the crossing take? In the early 1990s, a German physicist named Günther Nimtz, working at the University of Cologne, decided to measure the tunneling time for microwave photons crossing a region of space where normal electromagnetic propagation was forbidden. The electromagnetic analog of quantum tunneling, a region where the wave cannot propagate normally and instead decays exponentially. Precisely the tunneling situation translated into the language of classical waves. Nimtz sent microwave signals through a barrier approximately 100 millimeters long and carefully compared the time taken by the tunneling signal to the time taken by a signal traveling the same distance through open air. A measurable feature of the tunneling signal appeared to arrive at the detector before a signal traveling at the speed of light would have completed the same crossing. By a margin consistent with an apparent propagation velocity several times the speed of light. He verified the result multiple times. He changed the frequency. He changed the barrier geometry. The effect persisted. And then, in a step that gave the experiment a quality no dry physics paper usually possesses, he encoded a recording of Mozart in the microwave signal, sent it through the tunneling barrier, and showed that the music arrived recognizable and intact at the far side, before a light-speed signal would have completed the crossing. The physics community argued about this for years. The mainstream interpretation held that what Nimtz had measured was not the velocity of information, but a mathematical property of the wave, one of several distinct velocities associated with any wave, not all of which carry information in the way the word velocity normally implies. In the anomalous propagation conditions NIMPS was working with, certain wave features can appear to travel superluminally, while the boundary carrying genuinely new information remains at or below the speed of light. NIMPS disagreed. He argued that modulated music constituted real information and had genuinely traveled faster than light. The exchange between NIMPS and his critics was conducted seriously, in peer-reviewed journals, without reaching a consensus that satisfied everyone. Rest here for a moment. A physicist played Mozart through a barrier. The music appeared to arrive before light would have. And serious physicists have been arguing about what that means for 3 decades. What the controversy clarified was something important about the structure of the question itself. Whether faster than light travel is possible depends very precisely on what you mean by travel. By faster, and by light speed. In unusual physical regimes, these concepts do not always separate cleanly. And that ambiguity, sitting in the data from a real experiment with real instruments, is more interesting than either a clean confirmation or a clean refutation would have been. The question remained active. In the year 2020, a team at the University of Toronto, led by Alcubierre Steinberg, published a measurement in the journal Nature of the time that rubidium atoms spent tunneling through a laser barrier, using a technique called weak measurement that probed the tunneling time without destroying the quantum state being studied. Their result found a finite and measurable tunneling time and reignited the discussion about what that time implies for the effective behavior of quantum particles in forbidden regions. The paper did not claim faster than light propagation. It established that the tunneling time question was not closed. The wall, in this corner of physics, is not as clean as the textbooks suggest. The surface has texture, and the experiment in New Jersey, the one involving a beam of light and a number that should not have been possible, took the ambiguity further still. The year 2000 was not expected to be a landmark year for fundamental physics. The major discoveries of the late 20th century had already happened. The confirmation of quarks, the detection of neutrino mass, the discovery that the expansion of the universe was accelerating. Physics was in a period of careful consolidation. The idea that a small team in a New Jersey laboratory would produce a result that appeared on the front page of the New York Times, a result that physicists would argue about for years, was not in anyone's forecast. The team was led by Lijun Wang, a physicist at the NEC Research Institute in Princeton. The experiment involved a glass cell approximately 6 centimeters long, filled with cesium gas prepared in a specific quantum state using lasers. Wang and his colleagues sent a pulse of light through the prepared cesium gas and measured the time of arrival at the far side, comparing it to the time a light pulse would take to travel the same distance through open air. The peak of the output pulse emerged from the far side of the cesium cell before the peak of the input pulse had finished entering it. A measurable feature of the pulse appeared to propagate through the medium at approximately 310 times the speed of light in vacuum. 310 times, c. In a controlled laboratory, measured with precision instruments, published in the journal Nature in July of the year 2000. After peer review, the press responded as the press responds to numbers like that. Headlines announced that Einstein had been wrong. The coverage was vivid and largely disconnected from what the experiment had actually shown. The physics community read the paper more carefully. What Wang had measured was the group velocity of the pulse. In the anomalously dispersive medium that the laser-prepared cesium gas created, the leading edge of the incoming pulse interacted with the prepared quantum state of the atoms and stimulated the reconstruction of the output pulse at the far side. With its peak advanced in time relative to simple propagation, the medium anticipated the shape of the pulse from information already encoded in its prepared state. No information traveled faster than light. Wang himself was clear about this in the paper and in subsequent interviews. But here is what the experiment genuinely demonstrated. The behavior of light in certain prepared media is strange enough that a measurable feature of a light pulse can appear to propagate at 310 times the speed of light in vacuum in a carefully controlled laboratory, published in one of the most rigorous scientific journals in the world. Without violating the known laws of physics, the intuition that light always behaves in a simple, predictable way is wrong. In unusual media, light does unusual things. Some of those unusual things produce numbers that sit uncomfortably close to questions about the nature of the speed limit itself. Let that sit with you for a moment. 310 times the speed of light. In a glass cell in New Jersey. Real. Confirmed. And not a violation of anything. The wall is standing, but the material it is made of, examined up close, is not uniform all the way through. In the spring of 1935, Albert Einstein sat down with two colleagues, Boris Podolsky and Nathan Rosen, and wrote a paper designed to prove that quantum mechanics was incomplete. The argument was precise. When two particles interact in certain ways, their quantum states become linked, entangled. After the interaction, measuring one particle determines the corresponding property of the other, regardless of the distance between them. Measure the spin of one entangled particle and find it pointing up, and its partner will be found pointing down, not after a delay, not after a signal has traveled. In the same moment, Einstein, Podolsky, and Rosen argued that this was unacceptable. Either the measurement of one particle was sending a signal to the other faster than light, violating special relativity, or the particles had possessed definite properties all along that quantum mechanics simply failed to describe. They called these unaccounted properties hidden variables and published their argument as evidence that quantum mechanics needed to be completed by a deeper theory. They published and waited for the physics community to fix the theory. The theory was not fixed. What happened instead was stranger. In the year 1964, a physicist named John Bell, working at CERN in Geneva, published a result that transformed the argument from philosophy into something an experiment could decide. Bell showed mathematically that hidden variable theories of the kind Einstein had imagined make different statistical predictions from standard quantum mechanics for certain types of experiments. He derived an inequality that any hidden variable theory must satisfy. Quantum mechanics predicted the inequality would be violated. An experiment could choose between them. The first serious experimental test was conducted by John Clauser and colleagues in Berkeley in the year 1972. The results favored quantum mechanics, but technical limitations left room for doubt. In the year 1982, Alain Aspect at the University of Paris conducted a more decisive experiment. Using pairs of photons measured at detectors far enough apart that no signal traveling at the speed of light could pass between them during the measurement. The results violated Bell's inequality by many standard deviations. Over the following decades, the experiments became more refined. In the year 2015, 3 independent teams working in the Netherlands, the United States, and Austria conducted loophole-free Bell tests. All 3 found the same result. Bell's inequality was violated. Hidden variables were ruled out. In the year 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for this work. The prize committee was precise. It did not say that faster-than-light communication had been demonstrated. It said that the correlations were real, and that they could not be explained by any theory in which the particles carried local hidden properties determined before the measurement. Can entanglement be used to send information faster than light? The mathematical answer is no. And the argument is exact. To use an entangled pair to communicate, you would need to choose what measurement to make and communicate that choice to the distant recipient. That communication requires a conventional channel limited to the speed of light. Without it, the correlations look like random noise. The no communication theorem, derived rigorously from quantum mechanics, establishes this, and yet, the correlations appear without any signal traveling between the particles, across tested distances, with theory predicting no distance limit. The universe is doing something across space that is not a transmission in any conventional sense. But that is also not nothing. Something that physics can calculate precisely and cannot yet explain deeply. Let that sit quietly for a moment. The correlations are real. No signal carries them. The explanation is not yet complete. Einstein spent years believing this feature of quantum mechanics indicated incompleteness. The experiments proved him wrong on that specific point. What is happening in entanglement is not hidden variables. It is something genuinely non-local, something that appears across space without traveling through it, and something that a century of physics has not yet fully accounted for. That gap between perfect calculation and incomplete understanding is exactly where the frontier of physics lives. Miguel Alcubierre will tell you, if you ask him, that he was thinking about science fiction when he wrote the paper. He was a graduate student in Cardiff, working on his doctorate in general relativity, and he was a fan of Star Trek. The warp drive of the television series was not defined with any mathematical precision. It was a narrative device, a way of getting the crew from one star system to another without spending the episode in transit. But the concept it pointed at was interesting: warping space-time rather than accelerating through it, using the flexibility of the fabric rather than pushing against its limits. Alcubierre asked a question that was either very naive or very precise. Not whether a warp drive was physically possible, something more specific. Whether the equations of general relativity admitted a solution that looked like one. He worked backward through Einstein's field equations. He defined the geometry he wanted first: a bubble of flat space-time moving through the universe. Space compressed in front, contracted toward the destination. Space expanded behind, stretched away from the origin. Inside the bubble, space-time undistorted. The occupants would feel nothing unusual. No acceleration pressing them into their seats. No tidal forces. No time dilation relative to the universe outside. They would simply be sitting still while the space around them moved. He then asked what distribution of energy and matter the right side of Einstein's equation required to produce this geometry. The solution he published in the journal Classical and Quantum Gravity in the year 1994 was 9 pages long, mathematically rigorous, and confirmed to be correct by colleagues who checked it. Not an approximation, not a sketch, a precise solution to Einstein's equations. In the same mathematical category as the solutions that describe black holes and the expansion of the universe itself, the physics community responded with respect and skepticism in equal measure. Respect because the mathematics was correct. Skepticism because of what the mathematics demanded. Working out what energy distribution Einstein's equation required to produce the bubble geometry, Alcubierre found the answer was exotic matter. Specifically, matter with negative energy density, a substance that would push space-time apart rather than pull it together, something that had never been observed in any laboratory in any useful quantity. Early calculations of how much exotic matter the bubble would require produced numbers so large they placed the proposal outside any framework where practical discussion could apply. The gap between a valid mathematical solution and a buildable machine was not a gap in engineering. It was a gap in fundamental physics. Alcubierre was candid about this from the beginning. He had not proposed a blueprint. He had found a solution to equations and reported it honestly, including its requirements. But then the problem of exotic matter led somewhere unexpected. It led directly to a small, strange, laboratory-confirmed phenomenon that had been sitting in the physics literature since the 1940s, quietly, waiting for someone to ask the right question about it. That phenomenon is what the next 2 chapters examine, and reaching it requires spending time with what empty space actually is, which turns out, when you look carefully, to be one of the stranger questions in modern physics. Close your eyes for a moment if you like. Picture the emptiest place you can imagine, a perfect vacuum, nothing inside, and then hold that picture, because what quantum field theory says about it is about to change what nothing means. There is a particular rhythm to discovery in physics. A result arrives. The community examines it. The full implications accumulate slowly, often over years. In papers that build on each other and in conversations at conferences where people work through the consequences more carefully than the original publication had time to do. The Alcubierre metric followed this rhythm. The most detailed early analysis of the energy requirements came from Michael Fenning and Lawrence Ford at Tufts University in the late 1990s. Fenning and Ford applied quantum inequalities to the problem. Quantum inequalities are constraints derived from quantum field theory, the framework that combines quantum mechanics with special relativity that limit how negative energy can be distributed in space and time. They are not engineering constraints. They are fundamental limits on what the physical vacuum allows. Applied to the Alcubierre bubble geometry, for a bubble large enough to contain a spacecraft moving at a velocity comparable to the speed of light, their calculation found that the required exotic matter had a magnitude of approximately 10 to the power of 64 kilograms. The observable universe contains roughly 10 to the power of 53 kilograms of ordinary matter. Let that comparison settle for a moment. The energy bill for the Alcubierre drive exceeded the total mass energy content of everything we can observe in any direction, to the limits of the observable cosmos, by a factor of 100 billion. When a number exceeds the mass of the visible universe by that margin, it places the proposal outside any framework where the word impractical applies. The Alcubierre drive, as originally specified, required more than the universe appeared to contain. This result moved the Alcubierre metric firmly into the background of theoretical physics. A valid mathematical solution, a physically irrelevant one, by any honest accounting. Then, in the year 2012, a physicist at NASA's Johnson Space Center named Harold White reopened the question through a geometric insight. White noticed that the energy requirements of the Alcubierre bubble depended sensitively on the shape of the bubble wall, specifically on the thickness of the region of distorted spacetime surrounding the flat interior. The original paper had used a particular wall profile. White found that by modifying the bubble shape, introducing an oscillating geometry rather than the original static shell, his calculations suggested the exotic matter requirement could be reduced by many orders of magnitude. His published estimate, presented at a joint propulsion conference in 2012, suggested a modified geometry might require exotic matter with a mass energy equivalent of approximately 500 kilograms. He was explicit and careful about his caveats. A theoretical calculation, dependent on geometric assumptions not independently verified, not resolving the fundamental question of whether exotic matter existed in accessible form, but 500 kilograms is a number a human mind can hold. The mass of a large motorcycle. It moved the conversation, at least mathematically, from flatly impossible to extraordinarily difficult. The physics community examined White's modification carefully. The consensus that emerged was that the geometric reduction was mathematically real, but that important questions remained. Whether the quantum inequality constraints identified by Fenning and Ford applied equally to the modified geometry, and whether exotic matter in any form existed at accessible scales, were questions the calculation did not answer. White proposed an experiment, not a warp drive, not a prototype, a laboratory experiment to test whether a carefully arranged electromagnetic field configuration could produce a measurable, if vanishingly small, distortion of spacetime, an attempt to probe, with real instruments, whether the physical basis for the metric had any connection to observable reality. The laboratory where this experiment was conducted was called Eagle Works, at Johnson Space Center in Houston. The central instrument was an interferometer, a device that measured differences in light travel time along two paths with extraordinary sensitivity. The idea was that if the right electromagnetic field configuration approximated, even at minuscule scale, the energy distribution that the Alcubierre geometry required, the spacetime in the vicinity of that field should be very slightly distorted, and the distortion should be detectable. The results that Eagle Works reported were cautious and qualified. White and his colleagues observed anomalous signals in their interferometer data, patterns that did not match baseline expectations. They described these results carefully, noting they could not immediately attribute the signals to known artifacts, and that further investigation was warranted. They did not claim a detection of spacetime distortion. The physics community engaged with these results through the process that such claims require, an analysis by researchers at the University of Maryland, published in the year 2016, argued that the observed signals were most likely caused by the interaction of the electromagnetic field with the optical components of the interferometer itself, an effect on the optical path length through the glass of the beam splitter rather than a space-time effect. Harold White left NASA in the year 2016 and continued related research at a private organization called the Limitless Space Institute. The Eagle Works program wound down without producing a confirmed result that the broader physics community recognized as a detection of anything connected to space-time distortion. What Eagle Works represented, honestly accounted for, was the first serious institutional attempt to take a theoretical space-time metric into a laboratory and probe its physical predictions with real instruments. The attempt did not produce a confirmed result. It did clarify what the next generation of experiments would need. What sources of artifact required control? What level of sensitivity was necessary? What the distance was between where instruments currently stood and where they would need to be to answer the question. And underneath all of these experiments, underneath the Alcubierre metric and the energy requirements and the interferometer in Houston, there is a question that connects them all to a physical phenomenon that has been confirmed in laboratories for decades. A phenomenon that represents the closest thing to exotic matter that experimental physics has ever actually produced. And reaching it requires understanding what the quantum vacuum actually is, which turns out to be one of the stranger things that modern physics has found. The answer to that question is waiting in the next chapter, and it begins not with a dramatic experiment, but with a Dutch physicist. A prediction made in the year 1948, and a force between two uncharged metal plates that should not, by any classical account, exist at all. Picture the emptiest place you can imagine. Not a quiet room, not a dark field at night. The emptiest place that physics can describe. A region of space from which every atom, every molecule, every particle of dust has been removed. A perfect vacuum, sealed from the outside universe, cooled to the lowest temperature thermodynamics permits. A place where, by every classical definition, there is nothing. Now hold that picture, because quantum field theory is about to tell you something about it that does not fit inside the classical definition of nothing at all. In quantum field theory, the framework that combines quantum mechanics with special relativity and that represents our most precise description of the subatomic world. The vacuum is not empty. It is the lowest energy state of every quantum field that permeates space. And lowest energy does not mean zero energy. The vacuum hums. It fluctuates. At every point in space, at every moment in time, virtual particles appear and annihilate in pairs. A ceaseless background of quantum activity that averages to zero over time but is never truly absent. The nothing is not nothing. It has structure. These fluctuations permeate all of space. Every frequency of electromagnetic radiation contributes to them. In open, unbounded space, all frequencies are present in all directions, and the result is a vacuum that exerts no net force on objects immersed in it. But now place two uncharged, parallel conducting plates very close together. The plates impose a boundary condition on the electromagnetic field between them. Only certain modes of the field can exist in the gap, specifically those whose wavelengths fit between the plates, the way standing waves fit between the walls of a resonating cavity. Electromagnetic modes, whose wavelengths are longer than the plate separation, cannot fit. They are excluded from the space between the plates. Outside the plates, no such restriction applies. All wavelengths are present in the open space on either side. The result is an asymmetry. The vacuum between the plates is quieter than the vacuum outside them. Its fluctuation spectrum is depleted. Its energy density is slightly lower than the energy density of the unrestricted vacuum beyond the plates. And that difference in energy density produces a force, a real, measurable force, pushing the plates toward each other. Not because of any charge, not because of any magnetic property, because the geometry of the boundaries has modified the quantum vacuum in the space between them. This is the Casimir effect. Rest here for a moment. Two metal plates, separated by nanometers, no charge between them. And yet a force exists, not because of anything on the plates, because of what the geometry has done to the nothing between them. The Casimir effect was predicted in the year 1948 by Dutch physicist Hendrik Casimir. It was confirmed in precision measurements by Stephen Lamoureux at the University of Washington in the year 1997, and subsequently confirmed to within 1% precision by Umar Mohideen and Anushree Roy in the year 1998. The Casimir effect is real. It is reproducible. It is one of the most precisely confirmed predictions in quantum field theory. What it demonstrates is this: the quantum vacuum is not uniform. Its properties depend on the geometry of the boundaries around it. Between conducting plates separated by nanometers, the vacuum is a different vacuum from the vacuum outside. It has fewer modes. It has lower energy density. It has, in a precise quantum mechanical sense, negative energy density relative to the unrestricted vacuum beyond the plates. This is not exotic matter in the sense of a substance you could collect and store. It is a geometry-dependent modification of the vacuum itself, produced by the boundary conditions imposed by the conducting surfaces, but it is real negative energy density in the mathematical sense that matters for discussions of what general relativity requires. Not hypothetical, not theoretical, measured, confirmed, and reproducible on a laboratory bench. The Casimir effect does not give us a warp drive. The force between the plates is real, but it is relevant only at nanometer scales, and the total energy involved in any macroscopic Casimir apparatus is negligible compared to what even the most optimistic warp drive calculations require. The gap between what the Casimir effect demonstrates and what a warp bubble would require remains, by any honest accounting, many orders of magnitude. But the Casimir effect gives the discussion something it had previously lacked: a confirmed, laboratory-verified instance of negative energy density in the physical universe. It establishes that the ingredient the Alcubierre metric requires is not categorically absent from nature. The universe does produce negative energy density in specific geometries, under specific conditions. That foothold is narrow. It does not bridge the gap to a warp drive, but it changes the character of the question, from pure speculation to a question with at least one confirmed physical anchor in the laboratory. And there is more. In the year 2011, a team at Chalmers University of Technology in Sweden, led by Christopher Wilson, published a confirmation of a phenomenon predicted theoretically in the 1970s. Using a superconducting circuit whose effective electrical length could be modulated at microwave frequencies, creating the electromagnetic equivalent of a mirror moving at a significant fraction of the speed of light. They demonstrated that a moving boundary could cause the quantum vacuum to emit real, measurable photons, not virtual particles, not a theoretical prediction, real photons, produced from the vacuum itself by the motion of a boundary. This is called the dynamical Casimir effect. The vacuum can be excited. It responds to changing geometry by producing real radiation. The boundary between the vacuum as a passive background and the vacuum as something that participates actively in physical processes is a boundary that experiment has crossed. Let that settle for a moment. Moving a surface fast enough causes the vacuum of empty space to produce light. The nothing, disturbed, glows, whether vacuum engineering of greater sophistication, configurations more complex than parallel plates or oscillating circuits, might produce negative energy distributions. Relevant to space-time, geometry is an open theoretical question. Papers examining stacked Casimir geometries, periodic boundary structures, and resonant cavity configurations have appeared in journals, including Physical Review. They are theoretical. They make predictions that have not been experimentally confirmed. And here the honesty that tonight requires must be stated clearly. The gap between the confirmed Casimir results and anything that would matter for warp drive physics is not a small gap that ingenuity might close with better engineering. It is a gap of many orders of magnitude in energy, in scale, and in physical effect. The Casimir effect is the one confirmed anchor. It does not bring us close to the territory the Alcubierre metric requires. It establishes that the territory is not categorically forbidden by nature. That is what the edge of physics looks like. Not a door open wide. A door confirmed to exist, with no key yet found to open it further. In the year 2001, a British aerospace engineer named Roger Scheuer filed a patent for a device he called the M drive, a closed, truncated cone made of copper, wider at one end than the other, sealed at both ends, with no moving parts and no exhaust of any kind. Inside the cone, microwaves would be reflected back and forth between the two ends, and Scheuer claimed that this reflection, confined within the asymmetric cavity, would produce a net thrust in one direction. The physics community identified the problem immediately. Newton's third law: a rocket produces thrust by expelling mass. The reaction to that expulsion pushes the rocket forward. Scheuer's device expelled nothing. The microwaves were entirely contained within the copper shell. A closed system cannot produce a net force on itself. The device should not work. And then people started testing it. A group at Northwestern Polytechnical University in China reported in the year 2008 that they had measured a small thrust from their own version. Then, in the year 2016, a team at NASA's Eagle Works laboratory published a peer-reviewed paper in the Journal of Propulsion and Power reporting a small but apparently real thrust from an M-drive device tested in a vacuum chamber. The thrust was tiny, the weight of a single sheet of paper resting on your fingertip, but it appeared in a peer-reviewed journal, and the public response was not calibrated to the size of the effect. Headlines announced that NASA had confirmed a physics-defying engine. Science journalists described implications for space travel that the data did not remotely support. Rest here for a moment. Notice what happened. A force, the weight of a sheet of paper, became a story about the future of interstellar travel. This gap between what data shows and what headlines say is worth understanding, because it repeats itself with anomalous results in physics. Recognizing the pattern is part of how you navigate a world full of extraordinary claims. The physics community's response was methodical. Several independent groups undertook their own tests. The most rigorous was conducted by Martin Tajmar's team at the Technical University of Dresden, who had built a reputation for careful, skeptical, experimental work on claimed anomalous thrust devices. Timer's results, published in stages across the years 2017 through 2021, told a consistent story. The initial measurements showed a small thrust, consistent with earlier reports. As the experimental controls improved, as better thermal shielding was added and more potential sources of artifact were identified and eliminated, the measured thrust decreased. In 2021, Tajmar's group published their conclusion. The thrust was traceable to thermal effects. The asymmetric heating of the apparatus by the microwaves inside it caused tiny mechanical deformations that the force sensor interpreted as thrust. When thermal effects were properly controlled and minimized, the thrust disappeared. The M drive did not work. The conservation of momentum was not violated. The effect that multiple groups had measured was real. Its origin was subtle, mundane, and took years of careful work to identify. This is science operating correctly. Not dramatically, correctly. An anomalous result appears. Independent groups investigate with progressively improved controls. The investigation finds the explanation. The field moves on with better instruments and clearer understanding of where artifacts hide. The lesson the M drive leaves behind is worth carrying into every subsequent discussion of anomalous results in physics, including those later in tonight's journey. Peer review is the beginning of verification, not the end. An effect that appears in multiple laboratories but disappears when the controls improve is not evidence of new physics. It is evidence of a systematic artifact that the initial controls were insufficient to exclude. The instruments built and refined during the M drive investigation, force sensors of extraordinary sensitivity, thermal isolation techniques, vacuum apparatus designed to minimize mechanical coupling, represent a genuine contribution to experimental capability. The ghost was worth chasing. The chase built tools, and tools, in physics, have a way of finding uses their builders did not anticipate. The James Webb Space Telescope was not designed to find cracks in the speed of light. It was designed to see the first galaxies, to look back across 13 billion years of cosmic history to the period when the universe was young enough that the first stars were just beginning to ignite. It cost $10 billion. It took 30 years from initial concept to launch. It deployed itself over the following weeks through a sequence of approximately 344 individual mechanisms, each of which had to operate correctly in the vacuum of space with no possibility of human repair. If anything failed, everything worked. The images were extraordinary. Galaxies from the first billion years of cosmic history, more numerous and more fully formed than many models had predicted. The atmospheric chemistry of planets orbiting other stars. Read through the fingerprints that molecules leave in starlight. Stellar nurseries resolved into three-dimensional landscapes of light and shadow at scales no previous instrument could reach. But alongside the images, the telescope produced something less visually spectacular and considerably more troubling to the physicists analyzing it. A measurement of something already known, done with a precision that previous instruments could not match, a result that made an existing disagreement not smaller, more certain. The disagreement is called the Hubble tension, and it concerns something fundamental about how the universe expands. Two independent methods of measuring the universe's expansion rate have been producing different answers for years. The first method uses the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe uniformly in every direction. The Planck satellite, operated by the European Space Agency, mapped this background radiation with extraordinary precision and inferred an expansion rate of approximately 67 kilometers per second per megaparsec. For every unit of approximately 3.3 million light-years of distance, the universe expands at 67 kilometers per second. The second method uses the cosmic distance ladder, a chain of overlapping distance measurements reaching across billions of light-years. The research group, led by Adam Rees at Johns Hopkins University, which includes Nobel laureates and which has refined this measurement over many years, consistently finds an expansion rate of approximately 73 kilometers per second per megaparsec, 67 versus 73, a disagreement of approximately 9%. The measurements are now precise enough that this is not a matter of overlapping error bars. The disagreement has not shrunk as the instruments have improved. It has remained present, persistent, and statistically significant. The James Webb Space Telescope was deployed in part to help resolve the tension. Its superior resolution was expected to reveal whether the distance ladder measurements contained a systematic bias. A paper by Rees and colleagues, published in the Astrophysical Journal in the year 2023, using early James Webb data, reported that the Hubble measurements were not significantly biased. The distances held up under Webb's sharper scrutiny. The local expansion rate remained near 73. The microwave background value remained near 67. The tension did not dissolve. The James Webb data made it more certain. The statistical significance of the disagreement reached approximately 5 sigma, the threshold that particle physicists use to declare a discovery. The probability that this disagreement is a statistical fluctuation is less than 1 in 3.5 million. Rest here for a moment. The universe is expanding in a way that our two best measurement methods do not agree on. The disagreement is real. The explanation is not yet known. What does this mean for tonight's question? Here it is important to be precise. The Hubble tension is not a signal of faster-than-light phenomena. It is not evidence of a warp drive or a shortcut through space-time. It is something more foundational. It is evidence that our best current model of how space itself behaves over cosmic time may be missing something. Some ingredient, some physical process, some aspect of how space-time evolves. That current theory does not fully account for whether the missing ingredient is early dark energy, modified gravity at cosmological scales, new particles beyond those in the standard model, or something not yet proposed, is not known. All of these are active research programs. None has been confirmed. What the Hubble tension demonstrates is that the physics of space-time at the largest scales we can observe is not fully accounted for by our current best description. The model has a crack in it, not a crack in the speed of light, a crack in our understanding of how the fabric of space behaves over cosmic time. That crack may have a mundane explanation, or it may be pointing at something genuinely new. Sitting with that genuine uncertainty, without resolving it prematurely in either direction, is what the situation honestly requires. The universe, it turns out, has not finished surprising us about the way it expands. Everything we have examined tonight points back, eventually, to the same place, to the quantum vacuum, to the question of what empty space actually is, and whether that question has an answer that current physics has fully worked out. The Casimir effect confirmed that the vacuum is not uniform. Its properties depend on the geometry of the boundaries around it. Between conducting plates, the vacuum is modified in a measurable way. Its energy density is lower. A real force results, and the dynamical Casimir effect, confirmed at Chalmers University in 2011, established that the vacuum responds to motion as well as to static geometry, emitting real photons when boundaries move at sufficient speed. These are the confirmed experimental anchors. They establish that the quantum vacuum participates actively in physical processes and that its properties can be modified by geometry and motion. Now, the honesty that tonight requires must be stated directly. The gap between these confirmed results and anything that would be relevant to warp drive physics or faster-than-light travel is not a small gap. The Casimir force between two plates is a force measured in nanonewtons, the exotic matter required by the Alcubierre metric. Even in Harold White's most optimistic modified geometry, is measured in mass energy equivalents of hundreds of kilograms. The confirmed vacuum effects exist at scales many orders of magnitude removed from anything the Alcubierre geometry would require. This is not a gap that better engineering is obviously going to close. It is a gap in fundamental physics, between what the equations require and what the confirmed experiments have shown. That said, the theoretical question of whether configurations more complex than anything yet studied might produce vacuum effects at different scales is one that serious physicists have examined in peer-reviewed literature. Julian Schwinger, one of the founders of quantum electrodynamics and a Nobel laureate, spent the final years of his career investigating whether the Casimir effect might be connected to sonoluminescence, the emission of light from collapsing bubbles in liquid under sound pressure. His papers, published in the Proceedings of the National Academy of Sciences in the early 1990s, explored whether a rapidly collapsing spherical cavity might produce a Casimir-like modification of the vacuum at scales and intensities not accessible to static plate geometries. The connection he proposed did not achieve consensus acceptance, and the papers were contested, but they established that a Nobel laureate in quantum electrodynamics found the question of what happens to vacuum energy in dynamically changing geometries worth spending serious effort on. Let that sit for a moment. One of the founders of quantum electrodynamics, a man who had helped build the theory that describes this phenomenon, spent the final years of his career wondering if the Casimir effect was capable of things the simple two-plate version did not reveal. More recently, theoretical work on dynamic Casimir geometries has explored whether configurations beyond simple parallel plates might produce vacuum effects with different spatial distributions. Papers examining stacked Casimir geometries and resonant cavity configurations have appeared in journals including Physical Review and the European Physical Journal. These papers are theoretical. They make predictions that have not been experimentally confirmed. They sit at the edge of what current experimental physics can reach. There is a second thread connecting vacuum physics to the faster-than-light question, one that runs not through space-time geometry, but through the propagation of light itself. The speed of light in any medium is determined by the electromagnetic properties of that medium, its permittivity and its permeability. In ordinary vacuum, these properties have fixed values that produce the speed c. In any other medium, glass, water, a prepared atomic gas, these values differ, and the speed of light in that medium differs from c. The question that follows from the Casimir effect is whether the modified vacuum between conducting plates a vacuum with a depleted mode spectrum and lower energy density, has electromagnetic properties slightly different from ordinary vacuum. If it does, the speed of light inside a Casimir cavity would be slightly different from c in open space, not faster in the sense of violating special relativity, whose speed limit applies to the fundamental constant c itself, modified in the way that the speed of light is modified in any medium whose electromagnetic properties differ from those of ordinary vacuum. This question has been examined theoretically. Papers in journals, including Physical Review, have explored the electromagnetic properties of the Casimir vacuum and whether they differ from those of ordinary vacuum in ways that would affect light propagation. The theoretical picture is not yet fully settled. Some analyses suggest a small but non-zero effect. Others find the effect negligible within the approximations used. The experimental question of whether light propagation inside a Casimir cavity is measurably different from light propagation in open space has not been definitively answered with current instruments. This is the honest frontier, not a confirmed discovery, not a closed door, a question that the physics points toward, that the mathematics has begun to examine, and that the experiments have not yet reached with sufficient precision to resolve. Begin with a simple image. Two people, separated by an enormous distance, each holding one of a pair of entangled particles. They have agreed in advance on a code. Whatever result the first person measures, they will send a message to the second. Now imagine they also have access to a faster-than-light communication device, something that sends signals across any distance instantaneously. The first person measures, sends a message faster than light. The second person receives it. Now ask what that sequence looks like to a third observer, moving at high velocity relative to the other two. In the framework of special relativity, what appears instantaneous in one reference frame can appear to go backward in time in another. This is not a paradox unique to unusual physics. It is a direct mathematical consequence of the Lorentz transformations, the equations that describe how space and time coordinates change between reference frames, and it means that a faster-than-light signal in one reference frame is a signal that travels backward in time in some other reference frame. This was made precise in a paper by Gregory Benford, David Book, and William Newcomb, published in the year 1970. They described what they called the tachyonic antitelephone. A tachyon is a hypothetical particle that travels faster than light. Tachyons have never been observed. They may not exist. But working out what they would imply if they did reveals something important about the relationship between faster-than-light signals and the structure of time. The argument runs as follows. Observer A sends a faster-than-light signal to observer B, who is moving away from A at high velocity. In A's reference frame, the signal leaves at one moment and arrives at a later moment. Ordinary enough, just very fast. Apply the Lorentz transformation and shift to B's reference frame. In B's frame, the same signal arrives at B before it was sent by A. The signal has travelled backward in time in B's reference frame. Now B uses the same faster-than-light technology to send a reply. In B's frame, the reply travels forward. But transforming back to A's frame, the reply arrives at A before A sent the original signal. A receives a reply to a message it has not yet sent. The reply can contain information, decisions, Instructions derived from something that has not yet happened. This is not science fiction. It is a mathematical theorem about what faster-than-light signaling implies in a universe described by special relativity. Rest with that for a moment. A receives a reply before sending the message. The information is real. The loop has no consistent resolution within current physics. The Alcubierre warp bubble does not escape this. In the year 1996, a paper by Stanley Deser and Robert Levin showed that a sequence of warp bubbles used in the right configuration could construct a closed time-like curve, a path through space-time that loops back on itself and arrives at its own starting point before it departed. Alan Everett at Tufts University examined this conclusion in subsequent work and confirmed it. 2 warp drives used in a specific sequence produce, according to the mathematics of general relativity, the conditions for backward time travel. The warp drive and the time machine are, in the mathematics, the same device. Stephen Hawking thought about these questions carefully, and in the year 1992 proposed what he called the chronology protection conjecture. He argued that the laws of physics conspire to prevent the formation of closed time-like curves, that any physical configuration approaching the conditions for time travel would be destroyed by quantum effects before the time machine could form. Quantum field fluctuations near a region of spacetime on the verge of developing a closed time-like curve would amplify without limit, producing a divergence of energy that would destroy the region before the paradox could be realized. Hawking called it a conjecture because proving it rigorously would require a complete theory of quantum gravity, which does not exist. The conjecture is well motivated and supported by calculations in simplified models. It is not proven. What physics has, in place of a proof, is a pattern. Every mechanism proposed for faster-than-light travel, when examined carefully with the full toolkit of modern physics, encounters a problem that prevents its realization. The pattern is consistent. Whether it reflects a deep principle or a series of coincidental obstacles is genuinely unknown. What is known is that the faster-than-light question and the question of whether time has a consistent direction are not separable. They are the same question approached from 2 directions, and they cannot be resolved with current theories. Begin with a specific image. A crew sitting comfortably inside the flat interior of an Alcubierre bubble, midway through an interstellar journey. The bubble is working exactly as designed. Outside the bubble walls, space is compressed in front and expanded behind, and the entire structure is moving through the universe at many times the speed of light. Inside, everything is calm. No vibration, no acceleration, no radiation alarms. The instruments all read normal. Now ask what quantum field theory says is actually happening inside that calm interior. The answer arrives in a paper by Stefano Finazzi, Stefano Liberati, and Carlos Barcelo, published in Physical Review D in the year 2009. They analyzed the behavior of quantum fields in the Alcubierre geometry in detail. Their finding was that the bubble wall, the shell of extreme space-time curvature surrounding the flat interior, would cause the quantum vacuum to produce radiation through a process related to Hawking radiation. The phenomenon by which black holes slowly emit particles at their event horizons, unlike Hawking radiation from a black hole, which disperses outward into space. The radiation produced by the bubble wall would accumulate inside the bubble. The geometry traps it. The crew in the comfortable flat interior would be subjected to a growing flux of high-energy radiation produced not by anything outside, not by anything they can shield against, but by the bubble geometry itself. The radiation originates from the walls of their own vehicle and builds with every moment of travel. The Alcubierre drive is not a comfortable way to travel. It is an intensifying radiation environment. Let that image settle. The crew sits still. The instruments read normal. And the walls of the bubble are quietly generating radiation that accumulates around them, building with every light year crossed. The second problem concerns the arrival. When the bubble decelerates and stops at its destination, the radiation and particles that have accumulated at the forward edge during travel are released. For a bubble that has traveled interstellar distances at superluminal velocity, the energy released at the destination would be, depending on the specific journey parameters, comparable to or exceeding the energy of a very large nuclear detonation. Delivered to the point of arrival, the warp ship arrives. The destination is irradiated, not because something went wrong, because the geometry of the bubble, operating exactly as designed, builds up an energy concentration during travel that is released when the bubble stops. This is not an engineering problem with an engineering solution. It is a consequence of the space-time geometry and the behavior of quantum fields within it. The third problem is steering. Inside the bubble, the crew is surrounded by a wall of distorted space-time moving faster than light relative to the external universe. Any signal the crew sends toward the forward wall, even a light speed signal, cannot reach the forward wall before it has moved on. The crew cannot adjust the course. They cannot stop the bubble by sending a command to its leading edge. A warp bubble at superluminal velocity is, in a precise sense, unsteerable from the inside. Alcubierre has discussed these problems in subsequent work with the candor of a scientist who proposed a mathematical result and watched the community find its implications. The metric was not a blueprint. The physical properties of the solution, examined with the full toolkit of quantum field theory and general relativity working together, describe something that would harm its crew, irradiate its destination, and cannot be controlled during travel. These are not objections to the mathematics. The mathematics remains correct. They are discoveries about what the mathematics implies when it is followed carefully into territory the original paper did not explore. Whether a modified geometry, one that avoids these specific pathologies, exists within the space of solutions to general relativity and quantum field theory together, is an open question. It is the right question, but it cannot be answered with current physics. In the year 1895, Lord Kelvin, who established the absolute temperature scale that bears his name and made foundational contributions to thermodynamics, stated that heavier-than-air flying machines were impossible. He was applying the best physical understanding of his time to a question that engineers had been working on for years. The arguments seemed solid. The energy requirements, the structural demands, the control problem, all appeared to exceed what any practical machine could address. 8 years later, on a beach in North Carolina, Orville and Wilbur Wright flew. In the year 1933, Ernest Rutherford, who discovered the atomic nucleus, said publicly that anyone who expected to extract energy from the transformation of atoms was talking moonshine. The forces binding the nucleus were too strong. Practical nuclear energy was not serious physics. 12 years later, a device using exactly that principle ended the Second World War. These are not isolated examples chosen to manufacture a pattern. They are cases where technically sophisticated people, working with the best available information, concluded that specific things were physically impossible and were subsequently proven wrong. In each case, the physics they were using was not wrong. It was partial, and the partial picture produced a conclusion that the more complete picture overturned. Let that sit for a moment. Lord Kelvin was right about the aerodynamics he knew. He did not know about the Bernoulli effect applied to airfoils in the way that would enable lift. Rutherford was right about nuclear binding energy, as understood in 1933. He did not have access to the neutron-initiated fission process that would be conceived the following year. The physics was accurate. The picture was incomplete. The history of physics suggests that this happens consistently at the frontier, not occasionally. Consistently, every generation has things it considers settled, and a frontier where the settling is still happening. And the settled things have a way of becoming less settled when the frontier moves into them. This is not a license for wishful thinking. It is a more precise observation about what the word impossible means in physics, and what it has historically meant when applied to things that were actually in the category of not yet understood rather than genuinely prohibited. There are two kinds of impossible in physics. The first kind is impossible given current knowledge and technology. In a situation where the current knowledge is incomplete, and the incompleteness matters to the conclusion. This is the kind of impossible that heavier than air flight was in 1895. The physics was not wrong. It was partial. The second kind is impossible in a way that follows from principles so thoroughly tested, from so many independent directions, over such a long period, that the conclusion does not appear to rest on any assumption likely to be revised. The impossibility of a perpetual motion machine is this kind. The laws of thermodynamics have been tested across such a range of systems and conditions that the conclusion they imply is not a statement about current technology. It is a statement about the structure of the universe. Where does faster than light travel sit in this classification? The speed of light as a limit on the velocity of massive objects through space-time is extremely well established. The evidence for special relativity spans a century of independent measurements in particle physics, in atomic clocks, in GPS engineering, in the timing of signals to spacecraft. The core result is not going to be overturned, but the behavior of space-time itself, the behavior of the quantum vacuum, the relationship between quantum mechanics and general relativity in the regime, where both apply simultaneously. These are not established in the same sense. They are the frontier, the places where the map runs out. The Fermi Gamma Ray Space Telescope, launched in the year 2008, has been searching for evidence of quantum gravity effects by measuring the arrival times of photons at different energies from gamma ray bursts, the most energetic explosions in the observable universe. If quantum gravity modifies the dispersion relation of light, high-energy photons should travel very slightly differently from low-energy ones. And the difference, accumulated over billions of light-years, should be detectable. So far, the Fermi results have not found a signal. The constraints on quantum gravity modifications of light speed are now precise enough to rule out some of the simplest proposed theories. They have not ruled out all theories. The parameter space of what is possible is narrowing. In directions the data indicates are wrong. The space is closing. In directions the data has not yet reached. The space remains open. That is what the frontier looks like from the inside. Now, from this frontier, we turn to the honest accounting of everything tonight has covered, and what it actually adds up to. Let us set down everything we have carried through tonight, piece by piece, and look at what we actually brought back. The speed of light is real. The wall is real. A century of measurements from particle accelerators, from cesium atomic clocks on commercial airliners, from GPS satellites corrected daily for relativistic effects, from precision timing of signals to spacecraft at the edges of the solar system, all consistent with special relativity to a degree that places its core results among the most secure conclusions in all of science. Objects with mass cannot be accelerated to the speed of light through space. The energy required increases without limit as velocity approaches c. This is not going to change. Quantum tunneling is real. Particles cross barriers. They do not have sufficient energy to cross. Every moment. In the sun. In your devices. In the biological machinery of every living cell. Gunter Nimtz measured an anomalous propagation velocity in a tunneling microwave experiment and showed that a recording of Mozart appeared to arrive before a light-speed signal would have completed the same crossing. The mainstream interpretation says no information traveled faster than light. That what propagated superluminally was a mathematical feature of the wave rather than a signal. Nimtz argued otherwise for years. The University of Toronto experiment, published in Nature in 2020, confirmed that tunneling time is finite and measurable in ways that simple models do not fully capture. The conversation has not fully closed. A measurable feature of the light pulse in Li Junwang's cesium cell experiment appeared to propagate at approximately 310 times the speed of light in vacuum. Measured precisely. Published in Nature. Confirmed by peer review. No information traveled faster than light. The output pulse was a reconstruction by the medium, not a transmitted version of the input. The interpretation of what moved and at what velocity, at the level of precision that the faster-than-light question requires, remains an open discussion at the edges of the mainstream. Quantum entanglement is real. The correlations are real. They appear without any signal traveling between the particles, across tested distances, with theory predicting no distance limit. Confirmed by 3 independent, loophole-free experiments in 2015 and recognized by the Nobel Committee in 2022. No usable information travels faster than light through entanglement. Something is happening between entangled particles that does not travel through space in any conventional sense, that physics can calculate precisely and cannot yet explain deeply. The Alcubierre metric is real, a legitimate solution to Einstein's field equations. The exotic matter problem is real. Harold White's geometric modification reduced the energy requirements mathematically. The Eagle Works experiments produced anomalous signals attributed to optical artifacts by independent analysis in 2016. White left NASA in 2016. The Casimir effect is real. Confirmed since 1997. The dynamical Casimir effect is real. Confirmed at Chalmers University in 2011. The quantum vacuum has structure, responds to geometry and motion, and produces real, measurable effects. The gap between those confirmed effects and anything relevant to warp-drive physics is enormous and has not been bridged. The Hubble tension is real, persistent, and statistically significant beyond 5 sigma. It is evidence that our model of how space expands over cosmic time may be incomplete. It is not a signal of faster-than-light phenomena. This is what we actually have. The honest answer to the question in tonight's title is no. We have not discovered a real way to travel faster than light. The superluminal numbers that have appeared in experiments have explanations within current physics that do not require revising the speed limit. The Alcubierre metric describes a geometry that cannot be built with any material the universe is known to contain and whose physical properties, examined carefully, make it unusable, even in principle, with current understanding. The exotic matter problem has not been solved. The causality problems have not been resolved, but the honest answer has a second part. We have discovered, from several independent directions, that the universe is more complicated near its own speed limit than a simple statement of the limit suggests. The quantum vacuum has structure and can be modified by geometry and motion in ways that produce confirmed physical effects. The correlations in entanglement appear without any signal traveling between particles. The expansion of the universe is not fully accounted for by our best current model. The behavior of light in unusual media produces numbers that sit uncomfortably close to the questions this night has been following, without violating the laws that govern those questions. These are not the discoveries you would make in a universe where the speed of light was a simple, uninteresting boundary with nothing textured about it. They are the discoveries you make in a universe where the boundary has structure, where the vacuum has properties, where the geometry of space-time is flexible in ways that the simple statement of the speed limit does not fully capture. The wall is real. The surface of the wall is not smooth. And in physics, whenever the surface of a wall turns out not to be smooth, that is information about what the wall is made of that the original description did not include. What that information eventually implies, whether any configuration of space-time and vacuum and quantum field that no one has yet worked out might change the terms of the question, is not known. That is the honest position. Less dramatic than a discovery would be, more interesting than a closed door. There is something traveling away from you right now that you did not choose to send and cannot call back. It has been expanding outward since the first radio transmitters began operating. In the last years of the 19th century, a sphere of electromagnetic signal, growing larger every second at the speed of light, carrying in every direction the accumulated record of everything this civilization has broadcast into the air since it learned to do so. News, music, military radar, weather reports, television, the signal of a species learning to speak into the dark without quite deciding to. That sphere is now approximately 130 light-years across. Every star within 130 light-years of this planet has been reached by some portion of it. Whether that signal arrives with enough strength to be recognized or decoded is another question entirely, one that depends on the sensitivity of whatever instruments might be listening. But the signal has reached that far. The light went out, whether we intended it to or not. This is the thing about light that the whole of tonight has been pointing toward without quite saying directly. Among all the barriers we have examined, all the walls built from energy requirements and exotic matter and quantum instabilities and causality constraints, light passes through all of them without difficulty. Light has no mass. It pays nothing to the energy ledger. It does not accumulate radiation damage crossing the interstellar medium. It does not age. It does not require exotic matter. It does not violate causality. It travels at exactly the speed the universe has set as its maximum, and it does this across any distance, through any vacuum. For as long as the universe continues, the barriers we have spent tonight examining are barriers to mass. To anything that has weight and volume and the need for air and the fact of aging, light is not mass. It is a pattern. And patterns, it turns out, are what the universe is most willing to carry. Carl Sagan understood this. He spent a significant part of his career not on whether human bodies could cross the interstellar gulf, but on whether messages could. His novel Contact, published in 1985, imagined first contact arriving not as a ship descending from the sky, but as a signal in a radio telescope's data. A pattern in the noise that took time to recognize and longer to understand. The drama was not in the crossing. It was in the recognition, in the moment when a human being looked at a sequence of numbers and understood that the numbers had been arranged by a mind. Breathe in slowly here. Let that image settle. A pattern in noise. A sequence of numbers. And, in that sequence, the unmistakable shape of intention. Sagan also helped design the Voyager Golden Records, attached to both Voyager 1 and Voyager 2. They contain greetings in 55 human languages, music from cultures across every continent, the sounds of rain and wind and surf and whales, and a mother speaking to a newborn child. Encoded images of human beings and human structures, a map derived from the positions of known pulsars, precise enough that a civilization with the right knowledge could identify the origin. Voyager 1 is now more than 23 billion kilometers from the Sun. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space. In the year 2012, it is traveling at approximately 61,000 kilometers per hour. At that speed, pointed at the nearest star, it would arrive in approximately 73,000 years. But the radio signal from Voyager 1 travels at the speed of light. It crosses in hours the distance the spacecraft has spent nearly 50 years reaching. The pattern travels where the object cannot. The signal is the faster thing. By every measure relevant to communication, light has already solved the problem that mass cannot. The Breakthrough Listen program, launched in 2015, examines approximately 1 million nearby stars across a wide range of frequencies with sensitivity that exceeds all previous listening programs combined. It has not found a confirmed signal. The absence of a confirmed signal is information. It constrains the density of technological civilizations in our local volume of the galaxy. It does not close the search. The James Webb Space Telescope is reading the atmospheres of planets orbiting other stars, looking for chemical signatures of biology. Molecules like oxygen and methane, coexisting in a planetary atmosphere, would be difficult to explain without biological processes continuously producing them. The telescope has detected carbon dioxide and methane in the atmosphere of a planet called K2-18b, approximately 124 light-years distant. A preliminary analysis suggested the possible presence of dimethyl sulfide, a molecule produced on Earth almost exclusively by marine phytoplankton. Subsequent independent analyses have not confirmed this finding, and the scientific status of that specific detection remains uncertain. The search for more robust signatures continues, with each transit of the planet adding data to a measurement that requires patience and accumulation. Both of these programs are strategies for contact across a universe in which light is the fastest available channel. They do not require faster than light travel. They require patience, sensitivity, and the willingness to point instruments at the sky for years, waiting for something that may or may not be there. If we want to know what is out there. We do not need to go. We need to listen and to speak. The barriers that prevent mass from crossing the space between stars do not prevent information from crossing it. The search for signals is not a consolation prize for the failure to develop faster than light travel. It is the correct strategy, derived from the physics. For a universe where light is the one traveler, the walls cannot stop. Our letter is already out there. 130 light years of it, expanding in every direction. Whatever is within range of that expanding sphere, if anything is, has been reached by some portion of it. Whether anything has received it clearly enough to recognize, whether any reply is traveling toward us now, whether such a reply passed through this part of space before we had instruments sensitive enough to hear it, these are questions that physics cannot answer and that astronomy has not yet answered and that may be answered in any moment that has not yet arrived. The search continues. The instruments improve, and the sphere expands, adding to itself with every second that passes, carrying the record of everything we are into a darkness that extends in every direction farther than any of us will live to measure. That is not nothing. In a universe where mass cannot cross the gulf, information already has. Let everything go now. The equations, the laboratories, the names and numbers, and the careful distinctions between phase velocity and group velocity and signal velocity, let them drift back into the background where the things you encounter at night eventually settle, present somewhere beneath the surface. Available tomorrow if you want them. Quiet enough tonight that they do not interrupt the slower business of rest. Here is what can stay with you. Soft enough to carry into sleep without weight. Right now, somewhere, two metal plates are separated by a distance smaller than anything your eyes could see. Smaller than a bacterium. Smaller than a wavelength of visible light. Between those plates, the quantum vacuum of empty space is not the same as the vacuum everywhere else. It is quieter, depleted of the electromagnetic modes that cannot fit between such close boundaries. And that depletion produces a real, measured, confirmed force on the plates that bracket it. The nothing between those plates has structure, and in that structure, something about the relationship between space and energy is being revealed. One precision measurement at a time. To the people patient enough to keep measuring, right now, 1,000,000 miles from Earth, in the direction away from the Shun. A telescope with a gold-plated mirror is collecting the ancient light of distant worlds. It is reading that light for the chemical fingerprints of molecules that biology produces. It has not found a confirmed signature yet. The data accumulates with each transit of each planet. The answer is not yet in it. The telescope keeps turning. Right now, more than 23 billion kilometers from the Sun. A machine the size of a small car is moving through interstellar space. It has been moving for nearly 50 years without stopping. It carries, bolted to its side, a golden record containing the sounds of a world, chosen by people who thought carefully about what a stranger might need to understand who we were. The sounds of rain, the sounds of whales, music from 12 cultures, a mother speaking to a newborn child, a map home, encoded in the positions of stars. The machine cannot stop. It cannot be called back. It is going where the physics of its initial velocity sent it. Into the dark between the stars. Into the largest silence any human-made object has ever entered. Its radio signal travels home at the speed of light. The pattern arrives long before the object ever could. The pattern is always the faster thing. And right now, expanding outward from this planet at the speed of light. The electromagnetic record of more than a century of human transmission is moving through space in a sphere that grows larger with every second. It contains, somewhere in its expanding surface, the light of a night not unlike this one. A night when someone was lying in the dark and listening to a quiet voice explain the universe. And the explanation was traveling outward into the dark alongside everything else, carrying itself toward addresses that may or may not be home to anyone. At the only speed the universe has ever offered anything for free. You do not need to hold any of that tonight. The universe is not asking you to solve it. It has been sitting with these questions for 13.8 billion years, and it is in no hurry. It will still be asking in the morning, and the people whose work it is to ask alongside it will be back at their instruments when the light returns, checking the result again, the way careful people always check the things that matter. The wall is real. The surface of the wall is not smooth, and whatever lies on the other side of it, whether anyone will ever know, and how, and when, is the question that stays open when everything else tonight has finally closed. Let your breathing slow now. Let the galaxy continue its turning without you for a few hours. It has been doing it for billions of years without any assistance, and it is very good at it. The stars above you are very old. They are very far away, and they are, in the most precise and honest sense that physics currently allows, still not fully understood. That is enough. That is more than enough. Good night,